Welcome to Calculus. Today we will investigate how to use Euler's method to approximate differential equation solutions. We'll take a look at two examples. Our first example is this differential equation y prime equals x plus y. We want to use Euler's method to approximate solutions for the differential equation with a recursive process. We've seen something similar when we were trying to find zeros using Newton's method of approximation. We have to know our initial conditions. So in addition to the differential equation, I know that y at 0 equals 2. And then we have different intervals that we need to create. So in this case, we're going to create 10 different points. Our n value is 10, using the step of h equals 0.1. So a lot of information right there at the outset. Let's put it all together to make this approximation. So the way I want to start is I just want to define my successive x values. So I'm going to define x sub 0 first of all. And that's my initial condition. So x sub 0 I can see here is 0. And then as I go, I'm going to use my step value to increase the x value. So I'm adding to 0, 0.1. So x sub 1 is 0.1. X sub 2 would add another 0.1 to the value of x sub 1. So that's going to be 0.2. And you can see how that goes. At this point, x sub 3 would be 0.3, and so forth. ... We're going to go all the way up to using x sub 9. So at that point, what I want to do is define the algorithm that really is behind Euler's method. So I'm going to begin by approximating y sub 0. In fact, I'm not going to approximate y sub 0. I didn't know what y sub 0 is. It's 2. So where I'm going to begin is y sub 1. So let's just say how that is going to work generally, and then we'll fill in with some values. So y sub 1 is going to be equal to the previous y value, y sub 0. And I'm going to add to it the step value, h, times the function, which really is my differential equation, evaluated at the previous x and y values, so x sub 0 comma y sub 0. So that in a nutshell is how I would define each term, and we'll see how that kind of looks the same. The only thing that's going to change are the subscripts. But before we do so, let's actually fill in and calculate an approximation for y sub 1. So I know y sub 0 is 2, so I'm going to plug in 2. In fact, let's change here to blue so we see that there's a difference here. This is the actual values. 2 plus, my h value is fixed. It's 0.1. And then for the function, I actually need to pick up the right side of my differential equation. So that's defined as x plus y. So for us, our x sub 0 was 0. So that's 0 plus, and then y sub 0 is going to be 2. And that we would calculate out. So what I want to do is, in fact, this one's pretty easy to calculate. We can probably do it mentally, but then at some point, we're going to head over to the calculator and do most of our calculations there. In fact, we can kind of, once we see the pattern, we'll just use the calculator. But for this one, we can calculate manually. This is going to be 2 plus 0.1 times 0 plus 2 is 2. So that's 2 plus 0.2. That's going to be 2.2. Let's set up one more, and then we'll make that transition over to Desmos. So we're just going to write here so we see how would we get y sub 2. So again, it's recursive. I'm going to depend on the previous y value. So whereas in the first one we used y sub 0, here we're going to use y sub 1 plus h. Again, that h is fixed. It's always the same. Times the differential equation evaluated not at x sub 0, y sub 0, but x sub 1, y sub 1. So you can see how the recursive process takes us from one approximated y value to the next. And that's going to be the way we'll go the whole way. But let's actually fill in with the numbers here. So y sub 1 we had approximated to be 2.2 plus my h value of 0.1 times, in this case, x sub 1 plus y sub 1. So that's going to be 0.1. That's how I had defined x sub 1 at the outset, plus y sub 1, which we had just evaluated to be 2.2. So at that point, I want to go to the calculator, and really we're going to use the calculator kind of exclusively without all this setup to approximate up to y sub 10. We know we have to go to y sub 10 because our n value is 10. We got to have up to that many of them. But let's take this over to our Desmos. So I'm going to head over there, and I just really want to evaluate y sub 2 to begin. So here on Desmos, let's type in that expression that we just recorded. So it was 2.2 plus step value 0.1 times 0.1 plus 2.2. And that's giving us 2.43. Now at this point, instead of just kind of shuttling back and forth between writing the setup and calculating it, I can just keep going on Desmos. And the way it'll work is I'm going to take my, in this case, this is y sub 2. So now I want to calculate y sub 3. So I'm going to take y sub 2, add 0.1 times x sub 2, y sub 2 evaluated in the differential equation. So that's going to be 0.2 plus 2.43. And that's going to give me approximation 2.693. We'll keep going. So 2.693 plus 0.1. Again, I'm increasing the x value by the step of 0.1. So now we're at 0.3 plus 2.693. And that's calculating as 2.9923. And we continue this process. So I need to get up to a total of 10 values. So at this point, we are on our fifth one. This is going to be y sub 5. So I'm going to calculate that 2.9923 plus 0.1. Bump up the x value, 0.4 now, plus the y value I just approximated, 2.9923. That's going to give me 3.33153. Now for y sub 6, 3.33153 plus my step value 0.1. Bump up my x value by the step value of 0.1, so it's now 0.5 plus 3.33153. And that's giving me 3.714683. Now at this point, that's a lot to type. So here on the calculator, I can highlight that. In this case, that was y sub 5. I'm sorry, that was y sub 6. Now we want to calculate y sub 7, so I can just highlight it, copy it, and paste it. Plus 0.1. Bump up my x value by 0.1 plus what I just copied, and that's going to give me approximation 4.1462. So I could round these, but on the calculator, it's easy to highlight and copy. Here's my y sub 8. So I'll take the previous y value, so that was y sub 7, plus 0.1 times 0.7 plus y sub 7, which was 4.1462. And that's approximately 4.6308. And I'm going to copy that. And at this point, we're getting close to our final term here, our final approximation. So at that point, I'm going to type in, this is for y sub 9. So it's still 0.1 times now 0.8 plus what we just copied. So y sub 9 we would approximate as 5.1738. And our last value here, which is y sub 10, we'll copy y sub 9, paste it, plus 0.1 times 0.9 plus y sub 9. And the approximation there that we would get is 5.7812. Let's take it back to our, so I'm going to take all these values back and finalize here on our note screen. So we had our setup here. What I just want to do is give these values. So we started by calculating y sub 2, that was 2.43. Y sub 3, so we'll skip the setup. We've done all that already. Y sub 3 is 2.693. Y sub 4 is going to be 2.9923. And as these, so while I'm actually calculating, I try to include all the decimal values. When I'm reporting them here, though, I'm going to truncate them to 4 decimal places to the right. So as I get to y sub 5, I'll put that as 3.3315. I did have another digit in the calculation, but I'm going to just round there. Y sub 6, 3.7147. Y sub 7 is 4.1462. Y sub 8 from what we had calculated was 4.6308. 6308. Y sub 9 is 5.1738. And then for us, our last value on this approximation is going to be y sub 10, which is 5.7812. And that completes the approximation. So just to kind of keep in view, what did we just do? We approximated the particular solution for this differential equation, y prime equals x plus y, with the initial conditions of y at 0 equals 2. Why is that useful? To solve a differential equation like this, we just don't have the tools to do it yet. At this point in calculus, we haven't developed that strategy. And so Euler's method allows us a recursive algorithm to approximate the y values of a particular solution from the differential equation itself. It's a powerful tool without actually having to solve the differential equation. Well, let's take a look at our second example. So in our second example, what we want to do at this point is make a comparison and say, how do our approximations compare with y values that we would have in our exact solution? And then what would improve the approximation? How could we make it closer and closer and closer to the actual exact values? So I got a lot of instructions here. Let me jump directly to the question. I have my differential equation. This is in Leibniz notation, dy dx instead of the prime notation. Same thing. So dy dx equals 2x divided by y. And again, I've got an initial condition here that y when x is 0 is equal to 2. With this example, what's different though is I actually have the exact solution. So the exact solution for this equation is going to be y equals square root of 2x squared plus 4. And so what we want to do initially is we want to create a table that summarizes the values from the exact solution first, and then I want to run 2 different approximations using Euler's method with different step values. So before we kind of lose track of what we're doing, let me create that table first. So it's a horizontally aligned table, and I'm gonna put the X values first. So we'll start with 0. Told here to use these X values. So 0, 0.2, 4, 6, 8, and 1. So we'll go ahead and lay those out in a table format. And what I want to do first is I want to just evaluate the exact solution at those X values. So I'll put here, this is going to be y of X. And for my first version, this is going to be exact. So to do that, what I want to do is I want to take my exact solution, it's a particular solution there, and I want to just use Desmos to get me values for 0, 0.24 all the way up to 1. So let's do that right away here. We'll head over to our calculator. And I'm going to clear out, so you can see we got a lot of calculations from the recursive process. So I'm going to clear all that out. And I want to just input that solution. So that was given to us. We didn't have to solve it. In fact, at this point, we don't really know how to solve it. So we're grateful for this one. Y equals square root of 2x squared plus 4. So we can kind of see that's the particular solution that that we've got. It's got that curve there on the graph. And what I want to do is I want to get a table. So I'm going to click convert to table here. And I've got to modify my domain to match the X values that we had in our question. So I know I have 0. I need to include 0.1 and 0.2. And then, well, in fact, let me not get ahead of myself. We won't use that step value yet. We're going up by fifths to begin. So 0, 0.2, 0.4, 6, 8, and 1. So as you can see with Desmos, it's very quick, very convenient to just generate a table like that. So I'm going to record these values. At 0, we have the Y value of 2. 0.2 is 2.0199. 0.4, 2.0785 if I round. 0.6 is 2.1726. 0.8, 2.2978. And at 1, 2.4495. So let's take those back to our table and fill in. Keep in mind, those are not approximations. Those are exact values. The advantage as we kind of head into this process is this gives us a way to compare what makes our approximations better. So it gives us a control group. So I'm just going to put these values, I had written them down from Desmos, so 2.0199. At 0.4, it was 2.0785, 0.6, 2.1726, 0.8 was 2.2978, and at 1, 2.4495. So there's our baseline. Those are the exact values. What we want to do from here is run now 2 different approximations, real similarly to what we had done in the first question, but we're going to use different step values. So the first step value that we're going to use is 0.2. So we're told here in the instructions, use of an H value of 0.2. So I'm going to create another row here in my table, Y of X, and this is going to be specifically where my H value is 0.2. Now let's set some of those up. So I'm going to scroll down here just so that we don't interfere with our table, but I want to say how those are going to look. So we'll do that just the way we had done with our first example. So Y sub 0, we know is going to be 2. And again, I can say where that's coming from. That's from the initial condition, Y at 0 equals 2. Now we're going to use our algorithm, Euler's method, to proceed. So it's a recursive method. So Y sub 1 is going to be Y sub 0, which was 2, plus the step value. So here we're using a step value of 0.2. And then I want to take and evaluate in the differential equation using x sub 0, y sub 0. So that equation is 2x over y. So I'm going to put 2, and let me plug in my x sub 0. So x sub 0 was 0. So it'd be 2 times 0 divided by y sub 0, which again is 2. So I could take this to the calculator, but this one's pretty straightforward. This whole product here on the right, because it's got a 0 multiplying in there, is going to turn to 0. So this is 2 plus 0 is 2. So we can start to fill in. For this approximation, our first two values are 2. Let's set up for our y sub 2 and so forth, and then we'll, just like we did with our first example, we'll transition to Desmos to keep calculating. So again, I'm going to define this recursively. So y sub 2 equals y sub 1, which we just found was 2, plus the step value, which is for us now 0.2. Now the differential equation evaluated at x sub 1, y sub 1. So that's going to be 2 times, so x sub 1 is going to be 0.2 over y sub 1, which was 2. So again, I could probably do this on the calculator, but this is pretty quick to do manually. I see my 2's are going to cancel by division there in the fraction. And then in this product, what's left is 0.2 times 0.2, that's 0.04. And then add 2 to that, that's 2.04. So at this point, I kind of have the process set. I know what I'm looking at in terms of going from one term to the next. Once I've kind of got that in mind, what I'm going to do is, again, head over to the calculator as these values start to get larger in terms of their decimal expansion. So let's head over to Desmos, and what we'll do is we'll pick up, we had calculated y sub 2 there. Let's calculate y sub 3. So that's going to be y sub 2, 2.04 plus the step value of 0.2 times the differential equation. So it's 2 times my x value now is 0.4 over my previous y value, 2.04. And you can see it's getting very intensely decimal at this point. So I would round that as 2.1184, 2.1184. Just like we did in the first example, though, for the calculations, I'm going to copy and paste. It'll give me more accuracy. So I'm going to just kind of chug along here with the algorithm. So now my function differential equation is going to be 2 times x value 0.6 all over that value I had just pasted. And that gives us a y sub 4 value of 2.2317. Again, I'm going to continue on here. We got to do 2 more of these iterations. So I'm going to make sure I copied that. No, I highlighted it. Okay, paste it. So that's previous term plus 0.2 times the function, 2 times, now my x value has gone up to 0.8, and we'll put that all over at value 2.2317 ... And that, in fact, is our last calculation. I think I said we had 2. That's the last one. So 2.3751. Now, once I've calculated those, I want to take them back and fill in my table. And this will give us an initial comparison. How does my approximation compare to the exact values? So what we'll add to our table here, we had 2.04. At 0.6, we'll have an approximation of 2.1184. as 0.8, our approximation is 2.2317. And the last value we calculated there was 2.3751. So initially, our approximations we can see are pretty close. This is a good, fairly accurate method for approximating the solutions of a differential equation. But we're forced to ask, can we make it better? Can I in some way improve my accuracy? So let's see if a change in the step value will do that for us. So what I want to do is I want to now make a second approximation. So let's create this third row in our table. And what I'm going to do is I'm going to decrease my step size from 0.2 to 0.1. And you can see that's given to me in the instructions here. The second one, dropping my tools, is step value of 0.1. So we'll write that here. And again, we'll use our first couple values just to set our pattern. And then again, we'll head over to the calculator to complete the process. But let's set up here. So again, y sub 0 is going to be the same in each case. That's 2. So I'll put that there, 2. And then as I go here, my next calculation will not make it into the table because it's going to have an x value of 0.1. So we'll set it up. We have to do these intermediate calculations because the process is recursive. Each successive term depends on the one that came exactly before it. So we can't skip any, but we won't be reporting except half of them. So y sub 1 is going to be y sub 0, which was 2, plus the step value, which we've decreased to 0.1, times the function. So 2 times x sub 0, which was 0, over y sub 0, which was 2. So we're seeing the same thing here. That whole product quotient on the right cancels. This is just 2. But again, I'm not reporting that one. I'm only reporting every other one, since my table goes by 0.2 increments. So this is the one that we'll report next, y sub 2. So it'll be y sub 1, 2, plus the step value of 0.1 times the function 2 times, so my x value here is going to be 0.1. And that's going to all be over 2. So I think like we had done with our first example, well, the one that we calculated over here in the blue, I could actually calculate this manually because I got a cancellation 2 divided by 2. And then it's 0.1 times 0.1, so that'll be 0.01. Add that to 2, we got 2.01. And that is my next approximation, 2.01. So now once I've got that kind of in motion, I've set forth the recursive process, I can take this to the calculator. So let's head one last time back to Desmos. And let's calculate these values using the step of h equals 0.1. So where we had left off was y sub 2, and that was 2.01. So let's calculate y sub 3. Again, we won't use this one, but I need it to get to the next one, y sub 4, which we will use. So y sub 3 is going to be the previous term, 2.01, plus the step value of 0.1, times the function 2, our x value there is 0.2, all over 2.01. And that's going to give us a value of 2.030 if we were to round, or 2.0299. Now I'm going to continue my habit here of copying and pasting. So for my next term, which is y sub 4, we'll take that value, add to it again my fixed step value of 0.1 times the function. So now we're multiplying 2 times 0.3 over my y sub 3 value. And that's going to give me 2.0595. So that one will, in a moment, we'll take that back. We'll include that in our table. So we're only going to include every other one. That is one we'll include. That's y sub 4. Let's calculate y sub 5. So the thing is, if you have smaller step values, you have to calculate more. The previous approximation, we only had to calculate 5. Here we got to calculate 10. So we're kind of mid-process here. So again, I'm going to copy paste the previous term plus h value 0.1 times the function 2 times my x value is going to go up by 0.1, so 0.4 all over that previous term. So that approximation is going to be 2.0983. And again, I won't use that one. That's one of the intermediates. But I need it to get to the next one, which I will include in my table. So I'm going to copy paste and just kind of carry on with my algorithm here. 0.1 times the function 2 up by 0.1 for my x value, so 0.5, and paste that previous term in the denominator. So this I'll include, this is y sub 6, that's 2.1460. That's what I'll report. But again, to calculate now y sub 7, I'm going to copy paste. Keep going. Raise my x value by 0.1, so now 0.6 over that y value. That one we won't use, but we'll use it to calculate the next one, 2.2019 if I were to round. I'm going to copy the whole thing, paste it to calculate y sub 8. Add 0.1, our step value, times the differential equation, 2 times now 0.7 all over previous y value. So that one will include in our table 2.2655 when I round it. So we've got just a few more. It looks like we got 2 more. That was y sub 8 that we just calculated. So this is y sub 9. It's our last one that we will not use in our table, but again, I need it to get to the y sub 10. So now I'm at 0.8 over previous x value, previous y value, I'm sorry. So that final kind of intermediate calculation is going to be 2.3361. I'm going to copy it, paste it, and let's calculate our last one, y sub 10. Put my step value 0.1, 2 times now 0.9 over, oops, make sure we place that in the right spot. And that gives us our final value here, 2.4131. So as you're calculating these, you do want to write them down. You want to include all your setup on the work that you're doing. I've got all these written down. And what I'm going to do is take this back and let's fill in our table and then use the table to make some general claims. What would make an approximation closer and closer to the actual exact y values? So what we had calculated y sub 4 using the step value of h equals 0.1 is 2.0595. Now, what I'm noticing, even as I'm just filling in here, my first values were all the same. So there's no change in accuracy from the exact solution to the approximations. But when I go to my y values at 0.2 of x, the exact one's 2.0199. The approximation with step value 0.2 is 2. Approximation with step value 0.1 is 2.01. Which one's better? The smaller step value. So let's see if that is a common theme here. So I'm going to look at the next group of values. So when x is 0.4, and again, I'm seeing the same case. My exact value is 2.0785. When step value is 0.2, it's 2.04. When step value is 0.1, it's 2.0595. Still, my green value is closer, the one that we generated using a smaller step value. Let's see if that persists as a pattern here. So my next value that we had calculated with the 0.1 step value was 2.1460. And again, I'm seeing the same pattern there. This is closer to the exact value than the blue number, which we calculated using step value 0.2. Next one's 2.2655, same thing. This is closer to the exact value than the first approximation we'd run. And the last value confirms it, 2.4131, closer to the exact one than the step value that was larger. And that concludes our table. So again, that's all we're after here is we want to make a comparison. So to answer that question, what sort of H value gives a better approximation? A smaller and smaller H value. Well, thank you for joining for this investigation of using Euler's method to approximate differential equation solutions. See you soon.